Hello everyone, it's my pleasure to participate in this film. My name is Yongqi Ma and I'm from Shanghai Jiaotong University. Now let's give my report. My topic is experimental investigation of dynamic stability of a cantilevered pipe aspirating fluid. My presentation is divided into 4 parts. First of all, background. Second, experimental setup. 3, result and discussion. Finally, conclusions. First of all, as we all know, cantilevered pipe aspirating fluid are widely used in depth sea, meaning ocean thermal energy conversion, offshore oil industry. This fluid-induced vibration can be a serious problem that causes structure failure, resulting in environmental damage and economic loss. There are many research on vortex shading, wave acceleration, current, and platform motion, but there are few research on vibration caused by internal flow velocity in pipe. Second of all, 2 different diameters of the pipe were selected for internal pipe flow vibration experiment. The water pumped into the pipe through the experimental pipe, and then the water re-input the experimental pore through the flow transmit pipe. The pipe gets the energy from the internal flow fluid to generate vibration and record the tap displacement time history through the non-contact displacement sensor. The experimental setup built at Underwater Engineering Lab, Shanghai Jiaotong University, conducted a larger-scale water tank of length, width, and height of 5 meters. The oscillation frequency of amplitude of the pipe was measured through the change the pipe internal flow velocity. The test measuring instrument is mainly obtained by non-contact laser displacement sensor and water camera. We obtained the following conclusion from the experiment. This figure shows displacement of pipe 1 measured by the displacement transducer for internal flow velocity 3.2. For velocity 3.2, the pipe shows complex motion, switching between flat of considerable amplitude 1 minute to shutter motion the next. The amplitude and the frequency of obtuse motion significantly increase with the internal flow velocity increase. This figure shows time frequency analysis of the vibration response for a pipe 1. This figure shows shutter motion, and this figure B shows flat motion. From this figure, it is obtained that the response energy in the shutter vibration is low, and there is no large energy gathering at a certain frequency. The 2 figures shows the response energy concentrated at 0.42 Hz for the majority part of the cantilever pipe. It further confirms that the cantilevered pipe flat response is dominated by the first mode. From this figure, the internal flow excited response for the pipe is identified 3 regions: the static region, pre-instability region, post-instability region. For static region, the pipe still in a static state. 2. Pre-instability region, the pipe started to hard vibration, but the vibration amplitude is small. The post-instability region, the flatter critical velocity is is defined as a point of intersection of linear fatigue of the two regions, pre- and post-instability. This figure shows power spatial density of the displacement time series obtained at different flow velocity. From this figure, we obtain that the vibration frequency increases slightly with the increasing flow velocity. This phenomenon is because as internal flow velocity increases, more fluid energy is obtained at the free end of the pipe, which increases the vibration frequency of the pipe. The vibration frequency of the pipe increases slowly because of hydrodynamic drag caused by the surrounding water. This figure shows phase diagram at different internal velocity. From this figure, we can obtain that the typical near-period behavior in the range of internal velocity 2.1 to 2.5 in the regional pre-instability, and the pipe moved pendulum shape within this figure. The type of expansion behavior observed when internal velocity 3.4 to 3.7, the central part of ellipse in the phase diagram began to diffuse and began to expand, showing the development of sudden large amplitude motion. From this figure, we obtained that the vibration frequency of the pipe decreased as the submerged depth of the pipe increased for velocity, internal velocity 3.7. Most of energy is concentrated nearly the flood motion frequency, indicating that the instability performance of the pipe is dominated by the flood motion. The experimental result for the critical velocity with increasing pipe emerge length for pipe 1 and pipe 2, as presented in figure 15. From this figure, it is obtained that the critical velocity increases with increasing pipe emerging length. The main reason for this phenomenon is that the considerable hydrodynamic drag generated by the surrounding water to the pipe would damp out any small oscillation of the pipe. In summary, the main conclusion of the experimental are as follows. First, the pipe shows a complex motion consisting of two alternating phases, an approximately flat motion and a sharp motion with a small amplitude. 2. Internal flow excited response for the pipe is identified 3 regions: static region, pre-instability region, and the post-instability region. 3. The increase of flow velocity will increase the amplitude of the pipe motion, but will not quantitatively change the pipe motion. Finally, the fluid around the pipe will also affect the critical velocity. As the emerged depth of the pipe increased, the critical velocity of pipe also increased. That's all. Thank you for listening to my presentation.